Next, let's look at how to use the t-test command. So let's make up two arbitrary vectors. I'll make up x and y, and I can see them. There's x and there's y, just some numbers that I made up. The simplest way to run t-test is to say t.test x comma y, the two arguments of the two vectors that you're looking for. And if I do that, a bunch of stuff will be spit out. Got a t-statistic, giving me the degrees of freedom. We'll talk in a moment about why that is not a round number. And I've got a p-value. The default is a two-sided p-value. I've got a confidence interval, and I've got the two means in the two groups. Now the default is to do a Welch two-sample t-test, and that's why this word Welch is here right now. A t-test that does not assume the variances are equal. And we've said that when you don't assume the two variances are equal, the t-distribution is only approximately right, which is why we use a funny degrees of freedom here. If you know you have pairs, if we know that this 3 is somehow paired with this 2 and this 9 is somehow paired with this 0, then I want to say paired equals true. The default is for paired to be equal to false. Okay? If I do that, I get a slightly different p-value because it's taking into account the pairs. Or if I have a two-sample t-test and I actually do want to assume that the variances are equal, var.equal as a default is equal to false, which is why we by default get the Welch test. But if I set it equal to true, then I get yet another p-value. This is assuming that the variances are actually equal. You can see now the degrees of freedom is equal to a round number because when I assume the variances are equal, the t-test is not approximately but perfectly appropriate. There's another way to specify a test that is actually more parallel to the way other sorts of things such as regressions and ANOVAs are specified in R. Let's create a new vector w that's just equal to all of our outputs together, the x's and then after that the y's. So I'm concatenating the x's and the y's. W is now equal to those two vectors put together. And then I'm going to create another vector called group. So you can see that the group numbers 1 and 2 line up to the values of w. The first 4 values of w came from group 1. The second 4 values of w came from group 2. Why would we do that? Well, because now, equivalent to specifying t.test x comma y in R, I can say t.test vector of outcomes tilde, this is shift plus the button over the tab key, tilde group. That's exactly the same as saying t.test x comma y. Depending on how your data is set up, this or this may be easier, right? It's possible that your two sets of data points will come in two separate vectors, two separate columns, and then this is appropriate. But often you have one column that consists of all the values of the variable and another column telling you which group each of those is in, and then this format is going to be more appropriate. You can do the same thing for rank sum tests. So for Wilcox test, you can do x comma y or w tilde group. Here's another note. In R, you can take the variance. Suppose I take the variance of, I don't know, y. That's one of the vectors I have here. One important thing to note is this is the sample variance. In other words, this variance, y, is the sum of the squared differences between the values and the mean of the values divided by n minus 1. So the length of y here is 4. So this is those values, the sums of the squared differences divided by 3. If you want the true population variance, if the values in your vector are actually the population, then you need to multiply by n minus 1 over n to cancel out that n minus 1 in the denominator and put an n in the denominator. So when you use variance in R, it's by default giving you the sample variance. Why is it doing that? Well, because it's rare you'd have all the values in your population read into R so that you could take their variance. More commonly, the data points you have represent a sample. Here's a set of commands that are useful for calculating p-values. Suppose I've calculated a z-statistic, and my z-statistic is equal to -2. P-norm will tell me the probability that a standard normal distribution is less than or equal to the value I input. Right? So here it's -0.023 or so. If you want to, you can specify a mean and variance as part of p-norm so that this isn't the standard normal you're comparing it to. But in general, if you have a z-statistic, you can just type it in right there and find out the p-value. Similarly, pt will do the same thing. I could type in -2, but here I have to specify the degrees of freedom, right? And that'll give me the degrees of the p-value associated with the t-test. Now keep in mind, this is left-sided p-values only, right? This is the probability a standard normal is less than or equal to -2. This is the probability a t-distribution with 30 degrees of freedom is less than or equal to -2. if I want a two-sided p-value, I need to multiply these values by 2. Suppose my t-statistic was equal to 2 instead of negative 2. This quantity, or this command right here, is going to tell me the probability that a standard normal is less than 2, 97.7. Now what's my p-value? The p-value is the probability of getting something at least as extreme. And if I have a z-statistic of 2, then my value is way off on the right, and the one-sided p-value, the right-sided p-value, is actually 1 minus this quantity. And so the two-sided p-value would be 2 times 1 minus this quantity. And to see that, you can draw yourself a picture, and I also suggest playing with these commands.